You know that feeling. That one where you're really pushing right up against the edge of what's known, maybe in science, maybe trying to crack some tough engineering problem.
Yeah, that's definitely where the interesting stuff happens. And more, these advanced AI systems, well, they're not just watching from the sidelines anymore. They're actually getting involved, sometimes even driving the discovery.
Exactly. And today we are doing a deep dive into something pretty fascinating coming out of Google DeepMind. It's this new AI agent they're calling AlphaEvolve. We've been looking through the white paper they put out, some related notes too.
Right. So our goal here is really to unpack AlphaEvolve, figure out what it is, how it ticks, what makes it innovative. And honestly, the really exciting part is looking at some of the quite surprising things it's already managed to do.
And this isn't just theoretical, like you said. The sources are talking about breakthroughs in fundamental math, computer science, but also really significant practical improvements that Google's actually using in its own massive systems right now.
Okay, so let's dig in. What exactly is AlphaEvolve?
So the paper itself calls it an evolutionary coding agent. And they make a point right away. This isn't like just asking your standard large language model, your LLM, to write some code for you one time.
Right. Yeah, the keyword there is iterative. It's not a one-shot deal. Think of it more like an autonomous pipeline, maybe a whole system of LLMs that doesn't just spit out code, but keeps working on it, trying to improve existing code for whatever job you give it. And it does that by making direct changes, like edits to the code.
And the core engine driving this, like the name kind of suggests, is an evolutionary approach. It's constantly getting feedback, but the feedback comes from automated evaluators.
Exactly. And that feedback loop is absolutely critical. It lets the system refine an algorithm, over potentially thousands or millions of cycles, which is how it might just stumble onto something completely new, a real discovery.
And that whole process, the iterative feedback, that's what really makes it different from just asking a basic LLM for code, isn't it?
Totally. Instead of just guessing the next bit of code based on probability, AlphaEvolve is sort of grounded in reality. It uses actual code execution and gets automatic scores back. It tries something, sees if it worked or how well it worked based on hard numbers, and then uses that info for the next try.
Ah, okay. So it avoids, or at least can correct, those situations where a base LLM might just confidently suggest something that's actually wrong or just doesn't run.
Precisely. It helps filter out the bad ideas quickly because they just won't pass the evaluation stage.
Okay, so it's like this relentless inventor, not just brainstorming, but building and testing prototypes immediately. Let's trace that high-level flow they show in figures 1 and 2. It starts with a human setting things up, defining the what.
Correct. So you, as the user, you define the problem. That means setting up clear evaluation criteria. How does the system know if a solution is getting better? You also usually give it a starting point, like some initial code, maybe even pretty basic code. And you can also give it background info, like relevant math equations or links to research papers, stuff like that.
Okay, so the human sets the goalposts. Then AlphaEvolve steps in to figure out the how. It runs this evolutionary algorithm managing a whole population of potential code solutions, and it's all coordinated by this distributed controller loop.
Yeah, and inside that loop, a key part is the program database. You can think of it like a library storing every attempt, every idea it's generated and tested, along with the scores it got. It remembers what worked, what didn't.
Then they use an ensemble of LLMs, so multiple AI models working together. They look at a program pulled from that database and they generate changes, modifications.
Mhm.
Often they ask for these changes in a really specific format, like a diff, showing exactly what lines to add or delete or change.
Right, it's very structured.
Yeah.
And these changes get applied, creating a new version of the program code.
And then comes the critical bit. These new programs get sent straight to the evaluators. These are automated systems that actually run the code and score it using those criteria the humans set up at the start.
And those criteria, they have to be machine gradable, something you can automatically test and assign a number to, usually some metric you want to push higher.
And they mentioned this evaluation can be pretty flexible. It might be super fast, like seconds, or maybe it's complex and takes hours. But importantly, they can run these evaluations in parallel, right, across lots of machines.
Oh, absolutely. Parallel evaluation is key for throughput. Lets the system test tons of ideas without getting bottlenecked.
So the good solutions, the ones that score well, they get added back into that program database along with their scores and maybe other feedback. And that feeds the next cycle. It's just generate, test, learn, repeat.
Exactly. A continuous improvement loop.
What about integrating it with existing code? How does that work? Seems tricky.
It's actually pretty clever and simple. You just put special comments in your code, like hashtag evolve block start and hashtag evolve block end. Everything between those markers is fair game for AlphaEvolve to change. Everything outside is like the fixed skeleton, and the starting code inside the block. It can be really rudimentary.
Ah, okay. That makes sense. And they also talk about flexibility in the level of abstraction. What does that mean?
Right, so for the same underlying problem, you could set it up differently. You could have AlphaEvolve directly evolve the raw code text of a solution. Or you could have it evolve a function that builds the solution. Or, and this is really interesting, you could have it evolve a search algorithm that then goes and finds the solution.
Huh. Why choose different approaches?
Well, it depends on the problem. Sometimes, like if a problem has certain symmetries, evolving a constructor function might be more efficient. For other problems, as we'll see later, evolving the actual search process turned out to be the key to making breakthroughs.
Gotcha. And the prompts they feed these LLMs, they sound pretty packed.
They are. They leverage those huge context windows modern LLMs have. So the prompt includes things like previously successful code attempts from the database, system instructions telling the LM what to do, plus all that background context the user provided, equations, papers, whatever.
And they even mention it might evolve the prompt itself over time. That's pretty meta.
Yeah, potentially trying to figure out the best way to even ask for code modifications. And for the generation part, they use that ensemble Gemini 2.0 Flash and Pro. Flash is like the quick brainstormer, lots of ideas per second. Pro is maybe slower, but potentially comes up with higher quality, more breakthrough suggestions.
Using both makes sense, and asking for changes as diffs probably helps keep things focused.
Yeah, often it's easier to apply a targeted change than to regenerate a whole block of code and hope it still fits.
Okay, what about the evaluation side? Any cool features there?
Definitely. They can use something called an evaluation cascade. Think of it like a series of tests, starting easy and getting harder. Bad ideas get filtered out early on the simple tests, which saves a lot of computation time, rather than running the full expensive evaluation on everything.
Smart. Saves resources.
Yeah, and it can also incorporate feedback that isn't just a number. Like, they can use another LLM to look at the code and give feedback on, say, its simplicity or readability, even if that's hard to put a single score on.
And optimizing for multiple things at once. They say that helps.
It really does seem to. Even if you ultimately only care about one main score, optimizing for other metrics simultaneously helps maintain diversity in that program database.
Right.
It stops the system from getting stuck in one narrow area of the solution space, and sometimes that diversity actually helps it find even better solutions for your primary goal later on.
Okay, and the overall evolution strategy, how does it manage all these solutions?
It's basically managing that database to balance exploring brand new, maybe risky ideas with exploiting the best solutions found so far, trying to refine them further. They mentioned being inspired by established techniques from evolutionary computation, things like MAP elites and island models, which are designed precisely for maintaining diverse sets of high-performing options.
And the whole thing runs as a big asynchronous distributed pipeline optimized for throughput.
Exactly. Throughput is the name of the game. Maximize the number of ideas generated, executed, and evaluated within whatever time or compute budget you have. Because fundamentally, the more ideas you test, the better your chances of finding something really good, maybe even something completely novel.
Okay, wow. So that's the engine. This iterative, feedback-driven, code-evolving machine. It's pretty complex, but you can see the logic. Understanding how it works, though, I think makes the results they're recording even more incredible.
Right.
Let's pivot now to what AlphaEvolve has actually done. This is where it gets really interesting, because some of these results are genuinely surprising and have already had a big impact.
Yeah, let's start with something really fundamental in computing. Faster matrix multiplication. I mean, this operation is just everywhere. Machine learning, graphics, scientific simulations, you name it. Even tiny speedups here can ripple out and have massive effects downstream.
And we've known for ages, well, since Strawson back in 1969, that the standard way you learn in school isn't the fastest. You can do better by finding these clever ways to decompose the problem related to tensor decomposition. But finding the absolute best way, the minimum number of multiplications needed, that is notoriously difficult.
Incredibly hard. It's a problem that's basically stumped the best minds for decades. So AlphaEvolve was given this challenge. They started it off with a pretty standard algorithm that people use to search for these decompositions, something gradient-based. But then AlphaEvolve evolved that search algorithm itself into something much more sophisticated.
And the results?
Pretty staggering, honestly. The paper reports it improved the known state-of-the-art for 14 different matrix multiplication algorithms for various sizes and types. That's in Table 2.
But the big one, the headline result that really caught people's attention.
Right, multiplying 4x4 matrices with complex numbers. AlphaEvolve discovered an algorithm that does it using only 48 scalar multiplications. Now, you have to really appreciate this. That is the first improvement found for this specific problem size and type since Strassen's original discovery back in 1969.
Wow, after 56 years.
56 years. It just shows how hard these problems are and how this system could find something non-obvious that decades of human effort hadn't uncovered. And it's the general algorithm works over any field with characteristic 0.
How did it actually do it? What kind of changes did it make?
It wasn't just tiny tweaks. The paper shows in Figure 4 that it made about 15 significant non-trivial mutations to the original search program during its evolution. Things like changing the optimizer used, the initialization strategy, how the loss function was updated, even adding things like hyperparameter sweeps within the search. It really rebuilt the search process.
And it highlights maybe the potential for humans and AI working together too, right? Seeding it with good starting points.
Definitely. Okay, so moving from core computation to something maybe more abstract.
Yeah.
Solving open mathematical problems.
Right, this is frontier stuff. Mathematical research often involves finding specific objects or constructions that have optimal properties, or maybe just proving something exists by finding one example. Progress often hinges on finding just a single instance that's better than anything known before.
Exactly. So AlphaEvolve was applied to over 50 of these open problems, spanning different areas: analysis, combinatorics, number theory, geometry, a real mix. They typically started it with simple, sometimes even random initial constructions.
And the results there?
Really impressive again. In about 3/4 of the cases, 75%, it managed to rediscover the best constructions that were already known by mathematicians, which is a good sanity check, shows they can find known optimal. But then, in roughly 20% of the cases, it actually surpassed the state of the art. It found constructions that were better than anything previously published.
Wow. Any specific examples jump out?
Yeah, they mentioned a couple.
Yeah.
It improved the known bound for the minimum overlap problem, which is connected to work by the famous mathematician Paul Erdős. And it found a better construction for the kissing numbers problem in 11 dimensions. That's the problem of how many spheres you can pack around a central sphere so they all touch it. AlphaEvolve found a way to pack 593 spheres, beating the old record of 592.
Just one more sphere, but in these problems, finding that one extra is a huge deal. You can see some visuals of these in Figure 5, but how did it achieve this in math? Was it evolving the constructions directly?
This is a really key insight they found for these kinds of problems. Mostly, no. The big breakthroughs didn't come from evolving the mathematical objects themselves. Instead, AlphaEvolve was evolving heuristic search algorithms that were specifically good at finding those objects.
Okay, explain that distinction. That sounds important.
It's crucial. So the strategy wasn't evolve a better set of points. It was evolve a smarter process for finding a better set of points. Often this involved evolving heuristics that were good at taking an already decent solution, maybe found by some other method, and then iteratively refining it, making small changes to improve it further. AlphaEvolve essentially automated the discovery of these quite complex, multi-stage search and refinement strategies.
That's clever. It's like evolving the explorer, not just the map. And again, collaboration was key here too.
Yeah, they worked with external mathematicians like Javier Gomez Serrano and Terence Tao, who suggested problems and helped advise on how to frame them for the system. Another great example of that human-AI partnership potential.
Okay, so amazing results in fundamental math and CS. Now let's pivot to the real-world impact, applying this inside Google's own, massive computing ecosystem, optimizing actual production systems.
Right. And first up is data center scheduling. You can imagine, at Google scale, figuring out which computing jobs run on which physical machines in their Borg system. That's a nightmare optimization problem. If you do it badly, you end up with stranded resources. Maybe machine runs out of memory, but it still has loads of CPU power sitting idle.
Wasted capacity.
Exactly. And recovering even a small fraction of that across the whole fleet is incredibly valuable. So they frame this as a kind of complex bin packing problem. Jobs are items with different resource needs. CPU, memory, machines are bins. And the core of this system was a heuristic function that scores how suitable a machine is for a given job. AlphaEvolve's task: find a better scoring heuristic.
And did it?
It did. It discovered a heuristic function that, as shown in Figure 6, looks pretty simple on the surface, but turned out to be remarkably effective. They tested it rigorously using a data center simulator on real-world, unseen data, and it significantly beat the existing production heuristic.
And the bottom line?
When they rolled this evolved heuristic out across Google's global fleet, it consistently recovers an average of 0.7% of the entire fleet's compute resources that were previously stranded. Now, 0.7% might sound small, but given Google's scale, that's a massive amount of computing power reclaimed.
That's huge. And they also made a point about why they chose AlphaEvolve for this, right? Over something like deep reinforcement learning.
Yeah, that was interesting. They said for a mission-critical system like this, the heuristic function produced by AlphaEvolve was much more interpretable, easier to debug, and more predictable in its behavior compared to, say, a complex neural network policy from RL. Those factors are really important when you're managing something that vast and critical.
Makes sense. Okay, next up, helping out with Gemini itself. Gemini Kernel Engineering.
Right. So training these giant AI models like Gemini relies on super optimized low-level code, called kernels, that run efficiently on specialized hardware like Google's TPUs. A key part of this is optimizing tiling strategies for operations like matrix multiplication within these kernels, how you break down the big problem into smaller chunks for the hardware.
And that's normally hard.
Very hard and time-consuming. It's often done manually by expert engineers, which is slow. Or they use search-based methods, but those can be disruptive. The ideal goal is to have a good heuristic that can quickly determine a good tiling strategy for any input shape the kernel might encounter.
So AlphaEvolve to the rescue.
Exactly. They tasked it with optimizing the tiling heuristics for a key kernel used in training Gemini. The evaluation was simple. Just measure the actual runtime on real TPUs using input shapes representative of actual Gemini training workloads.
And the result?
It found a heuristic that led to an average 23% speed up for that specific kernel, which is great, but even better. That translated to a measurable 1% reduction in the overall training time for Gemini.
Wow, speeding up the training of one of the world's biggest models by 1% is significant.
It really is. And maybe just as importantly, it slashed the time needed for this kind of optimization. What used to take engineers months of tuning could now be done by AlphaEvolve in just days. That massively accelerates how quickly they can deploy improvements to the models.
And they highlight this as Gemini basically optimizing itself via AlphaEvolve.
Yeah, kind of a cool feedback loop there. And that evolved heuristic is now running in production.
Okay, third area, hardware circuit design. Actually designing the chips, like TPUs.
Yeah, this involves engineers writing descriptions of the hardware in languages like Verilog, this register transfer level or RTL code that goes through complex synthesis tools. But there's also a lot of manual optimization of the RTL itself, trying to reduce the chip's area or power consumption while ensuring it still functions correctly. This takes months and requires tons of verification.
So can AlphaEvolve optimize Verilog?
They gave it a shot. They challenged it to optimize an arithmetic circuit within a TPU design that human experts had already spent a lot of time optimizing. And AlphaEvolve actually found a simple code rewrite in the Verilog source that effectively removed some unnecessary bits from the calculation.
And this was a real improvement.
It was validated by the human TPU designers as correct and beneficial. Now, they do note that the later stage synthesis tools probably would have caught this particular optimization eventually. But the point was that AlphaEvolve found it directly at the source code level, the RTL.
Which could potentially save time earlier in the design cycle.
Exactly. And they framed this as Gemini's first direct contribution to TPU arithmetic circuits via AlphaEvolve. Plus, the fact that it outputs changes in Verilog that language engineers use makes it much easier for them to understand and potentially adopt.
Okay, one more practical application, optimizing compiler-generated code.
Right. So modern AI models heavily use things like the transformer architecture and optimize components like FlashAttention. These are often implemented as kernels. Compilers, like Google's XLA, take high-level code and translate it into lower-level intermediate representations, IRs, before generating the final machine code. Sometimes you can get extra performance by optimizing these IRs directly.
But that sounds really hard. Isn't that IR already supposed to be optimized by the compiler? And isn't it usually just for debugging?
It is hard for exactly those reasons. The IR is low-level, complex, and yeah, usually heavily optimized already.
Yeah.
But they pointed AlphaEvolve directly at the XLA-generated IR for the FlashAttention kernel, specifically for running inference on GPUs. The goal was simple: minimize execution time.
And even on this difficult target.
Impressively, yes. It managed to achieve a 32% speed up in the core FlashAttention kernel execution and a 15% speed up in the surrounding pre- and post-processing code just by rewriting parts of the IR.
That's a huge speed up for something like FlashAttention.
It really is.
Yeah.
Now, these IR level changes are complex and definitely needed expert verification to ensure they didn't break anything. But it shows AlphaEvolve can operate even at this very low level, finding optimizations that the compiler itself missed. And potentially, these kinds of discovered optimizations could eventually be fed back into the compilers themselves.
Making the compiler smarter for everyone.
Okay.
Okay, so we've seen how it works and these pretty amazing results across math, computer science, and real-world systems. Let's briefly touch on why this combination, the LLMs plus evolution plus feedback, seems to work so well. They did some ablation studies, right?
They did, yeah. Those are experiments where you basically turn off different parts of the system one by one to see what happens to performance. And the results shown in Figure 8 strongly suggest that you really need the whole package.
So it's not just one magic ingredient.
Doesn't seem like it. Performance drops off significantly if you take away the evolutionary approach, or if you don't give the LLMs enough context in their prompts, or if you restrict it from evolving the full code file, or if you use less capable base LLMs. It really looks like the synergy between the generative power of these SOTA LLMs and the rigorous iterative refinement from the evolutionary computation grounded by that machine feedback is key. It's more than the sum of its parts.
So putting AlphaEvolve in the bigger picture, it obviously builds on older ideas like genetic programming and maybe more recent things like fun search, which also used LLMs in evaluation. How does it differ?
It seems to differentiate itself by being able to evolve entire complex code bases directly, not just specific functions or snippets. Also, its ability to handle multiple optimization objectives simultaneously, and crucially, its integration of the very latest generation of LLMs with those massive context windows and sophisticated generative abilities.
And the paper really leans into this idea of surprising power emerging from that specific combination.
Absolutely. SOTA LLMs providing the creative spark, automated evaluation providing the ground truth, and the evolutionary framework providing the search strategy to navigate incredibly complex spaces. That combo is unlocking both these decades-old scientific problems and finding these really valuable practical optimizations that are just hard for humans to find or take too long.
And that flexibility we talked about earlier seems important too, being able to tackle a problem by evolving the solution or a constructor or the search algorithm itself.
Yeah, having multiple ways to frame the problem for the system seems like a major strength, letting it adapt to different kinds of challenges.
You could almost think of AlphaEvolve as a way to massively amplify the capability of a base LLM, right? Like adding this whole layer of pest-time compute through the evolutionary search and evaluation.
That's a great way to put it. It's not just using the LLM as it is, it's using computation during the problem-solving process to significantly boost what the underlying model can achieve. It's a powerful demonstration of scaling compute, not just for training models, but for actually using them to make discoveries.
What about the future? Where might this go? The paper hints at a few things.
Yeah, one really intriguing idea is trying to distill the insights or the improved performance discovered by AlphaEvolve back into future-based LLMs. Could you train the next generation of models to be inherently better because of what AlphaEvolve found? That's a cool research question.
Making the base model smarter from the start.
Exactly. And the other, maybe more immediate direction is just setting up more problems, finding more areas where you can define a robust automated evaluation function. The more problems we can frame in a way that AlphaEvolve can understand and get feedback on, the more opportunities there are for it to find these high-value discoveries, whether in science or industry.
But that does highlight the main limitation they mentioned, doesn't it? It really hinges on having that automated evaluator.
For sure. That's the bottleneck. There are loads of important problems, maybe especially in the natural sciences or complex design fields, where success isn't easily measured by a simple function. It might require running a physical experiment or getting subjective human feedback. Those are much harder to plug into this kind of system right now.
Although they did briefly mention maybe linking it up, starting with LLMs for high-level ideas, then maybe using AlphaEvolve once you can nail down a specific part with a clear evaluation.
Right, sort of a hybrid approach. Use LLMs for the fuzzy front end and AlphaEvolve for the rigorous optimization once a subproblem becomes well-defined enough. That could be a powerful combination too.
So wrapping this up, AlphaEvolve feels like more than just another AI paper. It seems like a genuinely powerful tool, something that's already broken barriers that stood for over half a century in math, and is actively making Google's own incredibly complex systems run better.
Yeah, it really demonstrates the potential you unlock when you combine these incredibly powerful generative models, the LLMs, with the relentless targeted search of evolutionary algorithms, and crucially, ground the whole thing in the real results you get from executing and evaluating the code automatically.
And I think the core idea that sticks with me is these AI systems, not just as code writers, but as autonomous agents that can evolve and optimize code guided by performance to actually make discoveries we didn't know before.
Which leads to a really interesting closing thought for you, the listener. Thinking about this power AI that iteratively improves solutions based on automated feedback, what other areas might be unlocked if we could just figure out how to frame the challenge with a clear automatic evaluation function? What problems maybe in your own field, your own work, could benefit from something like AlphaEvolve if only you could define precisely in code what success looks like?